Welcome to the deep dive. You've sent us a really fascinating collection of research all about how we learn when we look at visual information, specifically things like maps and diagrams.
It's a great topic.
Our goal today is to really get under the hood of how our brains process these tools so that you can become even better at, understanding information quickly and effectively think of it as upgrading your brain's visual learning software.
What's really interesting as we get started is this core idea.
hmm
Even though a map showing, say, the layout of a national park and a diagram illustrating how your car engine works are showing completely different things.
Right. One's real space, one's conceptual.
Exactly. One, a real physical space. The other, a set of conceptual relationships. It turns out they engage very similar processes in our minds. That's why it makes sense to look at them together, to boost your understanding of both.
Okay, so the research lays out this theoretical framework suggesting that maps and diagrams, despite their obvious differences in what they represent, share a fundamental way of using symbols. And it's this underlying symbol system that interacts with our thinking in surprisingly similar ways.
Precisely. And a key part of this interaction happens right at the beginning, almost instantly, before you're even consciously aware of it. We're talking about what are called pre-attentive processes, things your brain does automatically.
Automatically.
Yeah. The framework really focuses on two main players here. Configuration, which is how we automatically group elements together,
Grouping.
and discrimination, which is how easily we can tell those individual elements apart.
So if we can understand these pre-attentive processes, how our brains initially take in and organize visual information, that's really the first step in making visual learning from maps and diagrams much more effective for you.
Yeah,
It's like understanding the fundamentals before you try to master a complex skill.
exactly. The theoretical framework we're exploring here really builds on the work of a researcher named Salomon. He suggested that how well we learn from any kind of media isn't just about the information itself, but also about how the specific symbol system of that medium interacts with the way our brains work. Think about it. If you see a little drawing of a restaurant on a map instead of just the word restaurant, that visual symbol engages your brain differently and can lead to a stronger memory.
That totally makes sense. A quick image can trigger our visual memory in a way that a word sometimes just can't.
Right.
So to really understand how you learn from looking at maps and diagrams, we need to examine this back and forth between their visual language and our fundamental psychological processes.
And that's where these pre-attentive processes come into play. This initial processing is incredibly fast. It happens across your entire field of vision at once, and crucially, it's outside of your conscious control.
You can't control it.
You can't really decide to process this initial information differently. It just happens automatically. One researcher described these processes as being almost impenetrable to our conscious will.
Impenetrable. That's a great way to put it. So these automatic processes are really being driven by two key things in the map or diagram itself. First, the spatial relationships between all the different parts where things are in relation to each other. And that leads to configuration, how our brain groups things together. And second, how those individual parts actually look, their visual characteristics, and that affects discrimination, how easily we can tell them apart.
Right. Let's dive a little deeper into this idea of configuration. This is all about how your brain automatically takes the objects or ideas you're seeing and starts forming them into meaningful groups or clusters. It also influences the order in which you tend to process different elements and which ones are likely to grab your attention a bit later on. Think about seeing a cluster of stars in the night sky. Your brain immediately tries to find patterns and group them into constellations. It's a similar process with visual information on a page.
And then we have discrimination, the other crucial part of this initial processing. This is simply how easy it is for you to visually distinguish one element from another.
Yeah.
On a hiking map, is that trail marker clearly distinct from the symbol for a water source? In a complex diagram, is one component easily recognizable compared to all the others?
Exactly. And it's these very early pre-attentive processes of configuration and discrimination that really set the stage for how you consciously interpret the map or diagram later. They shape your initial perception and guide your subsequent understanding
Okay, they set the stage.
of the information being presented.
So we're talking about any visual way of showing objects or ideas and how they relate to each other. And the terms map and diagram in this research are actually quite broad.
Very broad indeed. When we talk about a map, we mean anything that represents a territory. This could be a detailed topographical map showing elevation, a simple street plan to help you navigate a city, a floor plan of a building so you know where the exits are,
Right.
or even a schematic map like you'd find for a subway system showing the connections between lines.
And diagrams are just as diverse. They're any kind of visual that uses space to show how different concepts are connected. Think about flowcharts that show a sequence of steps,
Yeah, or organizational charts.
organizational charts that illustrate hierarchies, diagrams that break down how a piece of text is structured, timelines that show events in order, even family trees that map out relationships.
Now, it's important to note that the research specifically excludes things like bar graphs and pie charts from this framework.
Why is that?
Well, that's because these types of visuals rely on a slightly different symbol system, primarily showing relationships between amounts or categories, rather than the spatial relationships we're really focusing on with maps and diagrams.
Okay, so we're focused on spatial representation. Got it. So, with this framework in mind, this idea of shared symbol systems and these key pre-attentive processes, what are some of the things it predicts about how we learn from looking at maps and diagrams?
Well, because we can so easily change how things are grouped together just by adjusting their spatial arrangement, the theory suggests that maps and diagrams are particularly effective at showing physical layouts, how things are positioned in space, how different parts connect, and how systems function.
Okay.
They can also act as really powerful mental organizers, almost like creating a mental blueprint or schema in your mind. This can help you structure information and make abstract ideas more concrete by tapping into your natural spatial reasoning abilities.
Right.
So for you, using a diagram to understand a complex process can be like having a mental model you can visualize and follow.
That makes a lot of sense. Seeing the structure of something laid out visually really helps solidify it in our minds. And what about the other side of the coin, manipulating how easily we can tell different elements apart? That's discrimination, right?
Yeah, discrimination. That leads to another set of predictions.
Yeah.
If you show objects or concepts as actual drawings, rather than just using abstract symbols or labels, it tends to make them more memorable.
More memorable. Okay.
Also, if you make certain elements really stand out visually by increasing their discriminability,
Oh.
it can definitely draw your attention to those specific details.
But is there a downside?
There is. Yeah, there's a potential trade-off here. You might focus so much on those highlighted details that you could miss the overall big picture of how everything fits together.
Okay.
And things like how familiar you are with the symbols, if they're ambiguous, the colors used, and even how visually appealing an element is can all influence where your attention goes and what you ultimately take away.
Interesting. So, a really striking, colorful symbol on a map might help me remember that specific location, but I might not immediately grasp how it relates to the surrounding area. It's about finding the right balance.
Exactly. Now, the research emphasizes that both maps and diagrams at their core use a common symbol system. They're both made up of individual components, things like symbols, labels, shapes, or even little pictures.
Components.
And these components are arranged in specific relationships to each other within the defined boundaries of the page or screen. Think about a map. You've got circled numbers for hiking trails, small blue shapes representing lakes, and the written names of towns. All of these are components within the map's overall border.
And if we look at a circuit diagram, the resistors, capacitors, and transistors, along with the lines that connect them, those are the components all contained within the diagram's frame.
Precisely.
Yeah.
And each of these components conveys information in essentially two main ways. First, it tells you something about what the component is itself, what it represents.
Okay, it's identity.
And second, it tells you about where it's located in relation to the overall map or diagram and in relation to all the other components around it.
So that circle 3 on the hiking map tells me it's a specific point of interest or a destination, and its location on the map tells me roughly where it is in the real world.
Right.
And in the circuit diagram, that zigzag line tells me it's a resistor, and its position and the lines connecting it show how it fits into the flow of electricity.
Right. And even with just these two ways of conveying information, you can create a surprising amount of complexity and detail simply by varying how these components and their relationships are displayed.
How so?
Well, for example, the location of a component can establish relationships both with the overall boundaries of the visual, is it at the top, bottom, left, or right, and with other nearby components, is it above, below, or next to something else. And as we'll see, these seemingly small variations in placement can have real implications for how we process and learn from the information.
And it's not just about absolute or relative position, but also the distance between components and the distance between a component and the edge of the visual, right?
Absolutely. Are things clustered closely together, or are they spread out across the page? All of these subtle spatial cues can influence our perception.
Okay.
Then we also need to think about the components themselves. One key aspect here is something called notationality.
Notationality.
Yeah. In notational systems, which most maps and diagrams are, there's a very clear one-to-one relationship between a symbol and what it represents in the real world or in the concept.
Like a legend on a map.
Exactly. The little cross symbol you often see on a map almost always means a church, and the standard symbol for a resistor in a circuit diagram consistently represents that specific electrical component. For you, high notationality means less guessing and quicker understanding.
That's different from something non-notational, like a photograph, I guess.
Exactly. In a photo, the connection between what you see and what it represents can be less direct. A shadow might obscure an important detail, or the natural colors might make it difficult to clearly distinguish different features.
It's not designed to be clear in the same way.
Precisely. Think about trying to understand the intricate workings of a computer just by looking at a photograph of its internal components.
Right.
It would be much harder than looking at a well-designed circuit diagram. The clear notationality of the symbols in the diagram makes it much easier to understand the structure and function.
Makes sense.
Components can also have varying degrees of dominance based on visual characteristics like their size, how isolated they are, or the colors used. A large, brightly colored symbol is naturally going to draw your eye and might be perceived as more important.
And then there's this idea of perceptual precedence. What our eyes and brains tend to notice first when you look at a map or a diagram. Do we see the overall layout first, or do we jump to the details?
Yeah, that's a good question. The research suggests it's not always a simple one-way street. There's an earlier idea called global precedence, which proposed that we always process the overall structure before we look at the finer details.
Big picture first.
Kind of. However, more recent findings point to what's called a middle-out account. This suggests that visual elements of an optimal size tend to be processed first.
Middle out,
Yeah.
not biggest or smallest.
Right, with both very small details and very large global configurations being processed slightly later. Factors like how long you're looking at the image and the specific visual properties of components within clusters can also influence what grabs your attention first. So for you, it means your brain might initially latch on to elements that are neither the biggest nor the smallest in the visual field.
Fascinating. So it's not just a straightforward top-down or bottom-up process. Our brains are more nuanced than that.
Precisely. Another shared aspect of map and diagram symbol systems is that the relationships between the components can convey a lot of information about both patterns and sequences.
Okay.
Think about a sailor using the two-dimensional pattern of landmarks on a nautical chart to pinpoint their exact location. That's relying on understanding spatial relationships in 2 dimensions.
Whereas a bus route map is more about the one-dimensional sequence of stops along a line, right? Even if the physical distances aren't drawn to scale.
Exactly. The order of the stops is what matters most for the passenger.
Right.
And an electrical engineer might look at a circuit diagram in 1 dimension to follow the connections between components, but also in 2 dimensions to think about optimizing the physical layout and the distances between components for better performance and efficiency.
Okay, so there are these fundamental similarities in how our brains process the symbol systems. But the research also points out some important differences between maps and diagrams in terms of what they actually represent.
Yes, most of these key differences relate to what the visuals are actually referring to. Maps almost always depict concrete objects and their locations within a real-world territory.
Literal space.
But diagrams have a broader scope. They can represent either concrete things, like the sequential steps in manufacturing process, or completely abstract concepts, like the hierarchical structure of a company.
Abstract concepts.
In these more abstract cases, the way components are visually presented and the spatial patterns they create are often metaphorical. For example, someone shown higher up on an organizational chart is understood to have more authority or influence, even though their vertical position on the page has nothing to do with their actual physical height.
This really clarifies why scale is absolutely crucial for maps. You need to understand the real-world distances and proportions, but it's often less critical in diagrams where the spatial relationships are more symbolic and representational rather than literal.
That's right. And this fundamental difference in what they represent also helps us understand why maps and diagrams might be interpreted in slightly different ways, even though our brains initially perceive and organize them using the same underlying psychological processes. So the research makes a distinction between the structure of the visual information, its syntax or configuration, how it's laid out, and its interpretation its semantics or meaning, what we understand from that layout.
So the structure is essentially the visual grammar of the map or diagram.
Yeah, like the grammar.
And the interpretation is how we, as viewers, decode that visual grammar to extract meaning.
Exactly. And a huge part of that initial visual grammar, as we've touched on, is this pre-attentive perceptual organization. This happens automatically before our conscious thought processes even really kick in.
That automatic stuff again.
Right. We're talking about how our brains configure basic visual elements into recognizable components and then automatically group those components into meaningful clusters. And of course, how easily we can visually discriminate one component from another.
These initial processes are happening almost simultaneously, even though we're discussing them in a step-by-step way for clarity.
Yeah, it's parallel.
And these pre-attentive processes really lay the groundwork. We can't even begin to consciously understand a map or diagram until these fundamental components have been configured into something recognizable. And we need to be able to tell the different visual elements apart before we can start categorizing the information or applying any rules based on what we see.
Precisely. And this pre-attentive configuration of components has been a significant area of research. One fundamental question is, what even counts as a single component at this very early stage of visual processing?
Like, what's the basic building block?
Exactly. Research suggests that individual parts of an image will configure into a single unified component when we can't easily focus our attention on each part separately. So even before you consciously think about it, you perceive a triangle as one distinct shape, not as three separate lines joined together.
Okay.
This is what's called an emergent property, where the whole becomes more significant than just the sum of its individual parts. For you, this means your brain is automatically looking for patterns in unified shapes right from the moment you see a visual.
And the physical distance between those parts really matters in this initial grouping, doesn't it? Proximity.
Absolutely. The closer individual elements are to each other, the more easily and readily they'll be seen as a single coherent component. And this principle extends to larger and more complex visual structures. The individual components within maps and diagrams can form hierarchical clusters, where smaller components group together to create larger, more meaningful units.
Like nested groups.
Exactly, which in turn can combine to form even bigger clusters. Think about a street map of a city. Individual buildings on a block form a cluster representing that city block, and then several adjacent blocks might be grouped together in your mind as a particular neighborhood or district.
And diagrams work in a very similar way, don't they? Like a science diagram.
Exactly. A diagram illustrating the water cycle might first present the key elements, water, oxygen, etc., then show the specific interactions and processes within each stage of the cycle, and finally provide detailed attributes of each individual element. It's like levels of organization within the visual.
Right, levels.
Exactly. And this early perceptual organization is heavily influenced by this hierarchical structure. Things that are close together visually tend to be associated with each other, forming distinct visual groups that can then be treated as single, unified pieces of information.
And boundaries matter too.
Yes. Even something as simple as a boundary line drawn around a group of closely positioned components can strongly reinforce the idea that they belong together and should be considered as a single unit. For you, paying attention to how elements are grouped visually can provide immediate clues about how they relate conceptually.
This sounds very similar to the idea of chunking information to make it easier for our working memory to handle and for us to remember later on.
It is indeed. Psychologists have long recognized that chunking, grouping individual pieces of information into larger, more meaningful units is a highly effective strategy for improving memory. Instead of trying to recall every single isolated detail, you only need to remember the larger chunk, and then you can often unpack the individual details within that chunk. And arranging information visually in clusters on a map or diagram directly supports and facilitates this natural chunking process.
The research highlights that this kind of visual chunking has been shown to be beneficial for all sorts of cognitive tasks, right? From remembering word lists to understanding circuit diagrams.
Absolutely. Remembering lists of seemingly unrelated words, recognizing complex letter patterns, recalling specific features on a map, understanding the structure of complicated layouts like spreadsheets and circuit diagrams. Even strategies for learning how to use maps and diagrams more effectively often involve this fundamental idea of chunking related visual information.
Okay, so chunking is key.
Exactly. Now let's shift our focus to the other crucial aspect of the initial visual structure, The discrimination of components, how easily we can visually distinguish one element from another.
Telling things apart.
Right. This is incredibly important because even before we consciously recognize what a particular symbol or visual element means, if different elements look very similar to each other, our brains will tend to associate them, potentially leading to confusion.
So, making sure that the different visual elements in a map or a diagram are visually distinct and easy to tell apart is a really important design principle for effective visual communication.
Absolutely. And there are several established visual techniques that can significantly facilitate this discrimination. Using distinct colors for different categories of information, employing a variety of shapes for different types of elements, varying the size of components to indicate relative importance, and controlling the overall level of visual complexity of each individual component. Research in the field of visual search has consistently shown that if you're trying to locate a specific item based on a single, unique visual feature, like finding a single red letter in a field of blue letters, it's a very fast, parallel, and almost automatic process for your brain.
Easy search.
Yeah. However, if you're searching for something that's defined by a combination of features, like trying to find a red X in a field containing both red and blue X's and Y's, the search process becomes much slower, more serial, and requires more of your conscious effort and attention.
That makes intuitive sense. The more different the thing you're looking for is in just one clear visual way, the quicker and easier it is to spot.
Exactly. And this leads to a somewhat surprising and counterintuitive finding from the research. If you increase the number of visual ways in which components within a map or diagram vary, it can actually make it harder for viewers to initially discriminate between them.
Wait, more variation makes it harder. How?
Well, for example, studies have shown that using highly detailed and intricate icons on battlefield maps or within complex computer interfaces can sometimes make it more difficult for users to quickly locate specific units or functions compared to using simpler, more conventional symbols. The increased visual complexity can actually overwhelm the initial discrimination process and slow down identification. So for you, more visual detail doesn't always equate to faster or better understanding, especially at first glance.
So more visual detail isn't always better when it comes to quickly finding and distinguishing different pieces of information. There can be a point of diminishing returns.
Not necessarily,
Yeah.
especially if the material you're looking at is new or unfamiliar. However, once you've had a chance to learn and internalize the meaning of those components, once you know what those more complex icons actually represent, then the negative impact of their complexity on discrimination tends to decrease.
Okay, familiarity helps.
Right. In fact, some research has even shown that for familiar map symbols, using more iconic or drawing-like representations can actually enhance your ability to recall them later. But the key takeaway is that for unfamiliar material, like encountering a circuit diagram with components you've never seen before, overly complex or visually similar icons can hinder your initial ability to discriminate between them, and can even divert your attention away from the overall structure and the relationships between the components.
Okay, so pre-attentively, the structure of a map or diagram is all about how the individual visual elements are grouped together and how easily they can be visually distinguished from one another. Configuration and discrimination.
Yeah, exactly.
Now, let's move on to the next stage. How we actually assign meaning to these visual structures once we start to pay conscious attention. How does the overall configuration of components influence what we ultimately understand?
This shifts us from that fast automatic processing to more of a top-down attentional processing mode. And the relationship between the configuration of visual elements and the meaning we derive from them has both psychological and cultural dimensions.
Okay, psychological and cultural.
Psychologically, we tend to read visual information in a way that's similar to how we read text, typically from left to right and from top to bottom in Western cultures.
Right, like reading a page.
The order in which we encounter different components on the page can really shape how we interpret their relationships and the overall message. So for you, your natural reading direction can subtly influence how you make sense of a visual layout.
And the cultural aspect is fascinating, isn't it? The research points out that the conventions we use in cartography and graphic design aren't universal.
Not at all.
They can vary significantly across different time periods and different cultures. Medieval maps, for example, weren't just about accurately representing geographical locations. They often incorporated historical events, religious symbolism, artistic embellishments.
Completely different purpose sometimes.
Yeah, leading to visual representations that look very different from the functional maps we use today.
Exactly. And studies have shown that people from different cultural backgrounds can sometimes interpret even relatively simple illustrations in surprisingly different ways, often applying their real-world perceptual habits and expectations in ways that can actually make understanding unfamiliar pictorial representations more difficult if they don't have a strong tradition of visual literacy for those specific types of images.
Right.
Even something as seemingly straightforward as how to visually depict an animal can vary considerably across cultures.
We also touched earlier on how the spatial arrangement of components itself conveys a significant amount of meaning. Location on the page can indicate absolute or relative position and even suggest a particular sequence or order.
Mm,
The research found that if you reverse what's considered a natural or conventional sequence in a diagram, for example, showing a process flowing from right to left instead of left to right, it can significantly hinder people's ability to recall the steps
yeah, it messes with expectations.
and even make it harder for them to correctly categorize the individual components.
Right. And there's a fairly common convention in many types of diagrams to visually place superordinate categories, the broader, more encompassing concepts above or to the left of subordinate categories, the more specific examples that fall under them.
General above specific.
Exactly. So in a hierarchical diagram, you might see animal positioned above mammal, which in turn would be above cat. If you reverse this conventional flow, it can make the diagram much more difficult to understand because you're encountering the specific examples before you have the general category to mentally place them within.
That makes sense.
Interestingly, even when diagrams were presented with this reverse flow, people's initial eye movements often still followed that ingrained left to right and top to bottom pattern, highlighting just how strong this reading direction bias can be.
Wow, even when it's wrong. The research also delved into how we interpret very simple two-component diagrams that used made-up nonsense words. What's fascinating is that even in these completely abstract cases, the way the two components were spatially arranged, whether they were side by side, one above the other, inside or outside of each other, etc., led to very clear and consistent biases in how people interpreted the relationship between those nonsense words.
Just the position told a story.
Yeah. Just the spatial configuration alone could suggest attributes, causal relationships, or even class membership. It really underscores how powerfully configuration shapes our interpretation of meaning.
Absolutely. Configuration is a remarkably powerful cue for meaning making. Now let's shift our focus slightly and consider how we understand the individual components themselves. What cognitive processes are involved in recognizing a single symbol or image within a map or diagram?
So we're moving from looking at the overall arrangement to focusing on how we identify the individual visual elements, component recognition.
Right. And there seems to be a general consensus in cognitive psychology that we recognize objects in pictures by identifying their constituent parts rather than relying on a holistic overall match.
Recognizing the parts.
Yeah. You don't need to see every single minute detail of a factory to recognize the standard symbol for a factory on a map, for example.
Right, just the key features.
That's right. Identifying just a few key characteristic features is often sufficient to trigger recognition. Your brain quickly compares the perceived parts to stored mental frameworks or schemata in your memory.
Schemata, okay.
Once a few key visual characteristics match the features stored in a particular schema, that schema is activated, and you're able to recognize and categorize the component. This parts-based approach is generally considered to be more efficient and flexible than older template matching theories, which would have required storing and comparing against a vast number of whole, complete images.
Too much storage needed for templates. And this process of visual recognition is very closely linked to how we learn concepts in general, right?
Exactly. Whether it's by identifying the essential, defining attributes of a category, or by recognizing a typical example or prototype of that category. The process of evaluating the critical visual attributes of a component against our existing mental schemata is what allows us to effectively recognize and understand the individual elements in maps and diagrams after we've initially discriminated them visually.
Okay, so that recognition builds on the earlier discrimination step.
Precisely. So that gives us a good overview of the theoretical framework that underpins how we learn from visual representations like maps and diagrams. It's a framework that's deeply rooted in fundamental research on perception, cognition, and how we process information.
Not just for education.
Not just specifically on the instructional use of visuals. But for this theory to be really useful for you, it should also be supported by actual research that has specifically investigated how we learn from these types of visuals. And that's where the second part of our deep dive takes us, looking at the research evidence.
Okay, so the theory makes some really interesting predictions about how our brains interact with the structure and individual elements of maps and diagrams. Now let's see how the actual research findings line up with these theoretical ideas.
Let's do it.
The article points out that while the underlying symbol systems of maps and diagrams share many similarities, there are also some important differences, especially when we consider how we process them with conscious attention.
Right. Maps tend to be more literal and realistic representations of actual physical territories,
Literal space again?
whereas diagrams often use space in a more analogical or metaphorical way to represent abstract concepts that we can't directly see.
Abstract concepts like influence or process flow.
Right. So a lot of the research on learning from maps focuses on skills like accurately estimating distances, developing navigational abilities, and interpreting literal spatial relationships within a represented environment.
Practical map skills.
On the other hand, research on diagrams often explores how this more metaphorical use of space can improve our memory and overall understanding of more abstract content that isn't tied to a physical location, such as understanding complex processes, organizational hierarchies, or the structure of arguments.
Let's start by looking at the research that specifically focuses on diagrams. The article highlights some really detailed work by researchers Larkin and Simon on how the specific configuration of components in a diagram can significantly improve comprehension, especially when you compare it to trying to learn the same information from purely textual descriptions.
Yeah, that's key work. What Larkin and Simon argued very convincingly is that two-dimensional diagrams have a fundamental advantage in conveying relational information compared to one-dimensional text.
Why is text less efficient?
Well, if you're trying to solve a problem or understand a complex concept from a purely text-based description, you often have to read through multiple sentences, identify the first piece of relevant information, hold it in your working memory, then search through the text to find the next related piece, and so on.
Lots of searching and holding.
Exactly. This sequential processing puts a significant load on your short-term memory and your search strategies, and it's quite easy to make errors or lose track of the connections. For you, this can mean slower comprehension and a greater chance of misunderstanding.
Whereas in a well-designed diagram, related pieces of information are often placed physically close together on the page.
Exactly.
Yeah.
So once you identify one relevant bit of information, the next piece you need is likely to be right there in your visual field. You don't have to mentally scan through a large amount of text or try to hold multiple disconnected facts in your memory at the same time because you can see the relationships visually laid out.
Less mental juggling.
Right. And this direct visual arrangement of related information can often make the underlying connections and the logical pathway to the next piece of information much more readily apparent than it would be in a linear text. This visual organization requires fewer cognitive resources, freeing up your mental capacity for actual comprehension and problem solving.
This idea of information being conveyed primarily through its spatial arrangement in a diagram, that's the visual argument concept.
Exactly. That's what has been called visual argument. Some researchers have even suggested that diagrams can express a fundamentally different kind of logic that is very difficult, if not impossible, to fully capture in text alone.
And there's quite a bit of evidence suggesting that our brains are particularly well suited to dealing with this kind of visual argument, right? The concept of mental models often comes up here.
Precisely. The idea that we use spatial relationships between different ideas in our minds to represent how we understand the world and how things work, well-designed diagrams can really facilitate the construction and refinement of accurate and useful mental models.
How do they do that?
By visually laying out the components and their relationships, diagrams provide a scaffold that helps you build a more coherent and integrated understanding of the information. And the research literature is full of examples illustrating this facilitation effect of diagrams across a wide range of subjects.
Like in social studies.
For instance, in social studies education, numerous studies have shown that adding a relevant diagram to textual material can significantly improve students' ability to recall and understand sequential and hierarchical relationships between concepts.
But just adding a diagram isn't always enough, is it?
No, that's a crucial point. The research consistently emphasizes that simply adding a diagram isn't always enough to guarantee improved learning. Often, the accompanying text itself needs to be carefully designed to explicitly refer to and explain the key features of the diagram for maximum educational impact.
Ah, the text needs to connect to the diagram.
Exactly. So for you, when encountering a diagram, it can be helpful to look for accompanying text that guides you through its key elements and relationships.
That makes perfect sense. The text can act as a guide, helping you to navigate and interpret the visual information presented in the diagram. And the research also points out an interesting nuance. The spatial information that's visually represented in a diagram isn't always encoded spatially in our minds.
That's a really important nuance to keep in mind. Sometimes we process and remember that information in a more propositional or descriptive way, almost like forming a verbal summary of the visual relationships.
So it's not always a direct visual memory.
Right. And it highlights the fact that effective learning from diagrams often involves an interplay between visual and verbal processing. It also underscores the point we touched on earlier, that instructional designers and educators should actively teach students specific strategies for how to effectively use and interpret diagrams.
Just giving them the picture isn't enough.
Exactly. Just providing the visual isn't a guarantee that learners will automatically know how to extract the most meaning from it.
Another powerful application of visual structure in learning is through the use of graphic organizers, which are essentially diagrams that provide an overarching framework or structure for the content being learned.
Yes, graphic organizers are great. The research has consistently found that these can significantly improve students' immediate comprehension of complex information compared to simply reading linear text.
How do they work?
They work by presenting the key concepts and their relationships simultaneously in a visual format. This allows students to build a mental schema or framework that they can then use to organize and integrate the more detailed information without feeling cognitively overwhelmed.
And timing matters, like
Yeah.
using them after learning.
Interestingly, yes. Some research suggests that graphic organizers that are presented after the initial instruction has taken place can be even more effective in promoting deeper learning, possibly because students are more actively engaged with trying to structure and make sense of the content at that point. This might be something for you to consider in your own learning. Try creating or looking at a summary diagram after you've initially encountered the information.
These graphic organizers sound very similar in principle to the idea of advanced organizers,
They are related, yeah.
which have a long history in instructional design as a way to prepare learners' minds for new information by providing a high-level conceptual overview. And the discussion also touches on the technique of text mapping,
Right. Visualizing text structure.
which involves using diagrams to visually represent the underlying structure of a written text, showing things like hierarchical relationships between ideas and semantic networks, illustrating how different vocabulary terms are connected.
And this has been shown to be a valuable tool for improving a wide range of literacy skills, from enhancing vocabulary development and facilitating note-taking to preparing for writing tasks and improving comprehension during and after reading.
So it helps with reading and writing.
Absolutely.
Yeah.
And it further reinforces the idea that using spatial analogies and visual representations can be incredibly effective for understanding and remembering more abstract concepts that aren't inherently visual themselves.
Like math concepts.
Exactly. This principle is also clearly evident in research on visualizing abstract mathematical concepts. Diagrams can be very powerful in making the often invisible relationships in mathematical problems more concrete and tangible, leading to significant improvements in problem-solving abilities. For example, using visual representations like drawn sets and operations has been shown to help students better understand addition and subtraction problems, and even employing computer graphics to visualize multiplication and division matrices can enhance learning in these areas. So spatial visualization isn't just limited to subjects like geometry. It has much broader applications.
And then there's the fascinating area of visualization in 3 dimensions, particularly when it comes to understanding complex structures like molecules.
Oh yeah, that's crucial in chemistry. Being able to mentally rotate and manipulate diagrams of these structures is a key skill. And the research has identified specific visual cues within these 3D diagrams that are absolutely key for accurately perceiving their configuration.
What kind of cues?
Yes, things like the degree of line foreshortening, the changes in angles between connected elements, the relative sizes of different parts of the molecule, and the phenomenon of occlusion, where one part of the structure visually hides another.
Occlusion,
Yeah.
like things blocking other things.
Exactly. They are all critical visual cues that your brain uses to infer the three-dimensional arrangement. If viewers don't effectively pick up on these visual cues, their understanding of the actual 3D structure can suffer significantly.
But you can teach people to see these cues.
Yes, absolutely. Research has also shown that instruction that explicitly teaches students how to process these depth cues, how to mentally rotate objects in 3 dimensions, and how to use reference frames within the diagrams can be really effective in improving their understanding across a wide range of ages.
What about specific techniques in the diagrams?
Techniques such as using shaded diagrams to enhance the perception of depth, presenting different rotations of the object simultaneously rather than successively, and strategically using color to highlight different parts of the structure have all been found to enhance learning from 3D visuals.
And animation helps too.
Yes, animation, which allows you to see the rotation or changes in dimension over time, has also been shown to improve understanding of complex orthographic drawings and can be particularly helpful in avoiding confusion that sometimes arises with static wireframe representations. This all ties back to our fundamental ability to form and mentally manipulate visual images in our minds.
Finally, in the realm of diagrams, the research also looks at how the specific nature of the individual components themselves, whether they are abstract symbols or more realistic drawings, can affect our attention and subsequent learning.
Right, the components again. For example, one study comparing flow diagrams that use simple labeled boxes versus those that incorporated more detailed drawings found that the diagrams with drawings often led to better recall of the information, particularly for students who had lower levels of prior academic ability.
Why would drawings help lower ability students more?
Well, this finding aligns well with Paivio's influential dual coding theory, which suggests that our brains encode visual information in 2 ways, both as a visual image and as a verbal description, whereas words are primarily encoded verbally.
2 codes are better than 1.
Exactly. This redundancy in encoding can provide an extra pathway for retrieval and can be especially beneficial for learners who may struggle with purely verbal processing. However, other research has indicated that the level of detail in the visual components can interact with how we process the overall structure of the diagram.
How so?
For instance, adding more detail to components in a diagram of dinosaur evolution aided recall of the sequence when the diagram followed a conventional left-to-right progression, but it didn't provide the same benefit when the diagram presented the sequence in a reversed order.
Interesting.
In that case, the direction of the depicted walking dinosaurs seemed to provide stronger cues for recalling the sequence. This highlights that how the components are presented can influence not only our recall of the details, but also our performance on specific tasks related to the diagram.
Okay, so the research on diagrams really highlights their power in conveying relationships, providing structure to complex information, and making abstract concepts more concrete and accessible. Now, let's turn our attention to maps.
Maps, right?
We know that maps are unique in that they represent real physical territories in a more or less realistic way, which requires a slightly different set of cognitive skills for interpretation. But how does the underlying theoretical framework about configuration and discrimination still apply?
Well, even though the specific skills involved in map reading differ somewhat, things like accurately estimating distances, interpreting symbolic representations of real-world features, and understanding literal spatial relationships.
Yeah.
The fundamental idea that information is encoded in cognitive schemata that then guide our interpretation still holds true. So when we look at maps and associated textual information, that information can be encoded in our memory both spatially, as the layout of the map, and verbally as the descriptive text.
Spatial and verbal encoding.
Yes. There's a body of research on what's called conjoint retention, which is similar to the dual coding idea we just discussed. It suggests that verbal and spatial information about a map and any related text are often stored separately in our memory, but we can access both types of information when we need to recall something.
Okay.
Studies have consistently shown that when the information presented on a map is congruent or aligns well with the content of a descriptive text about the same area, our recall of both the map features and the textual details is significantly improved.
Congruence helps recall.
Yeah. In fact, the spatial information derived from the map can even act as a retrieval cue to help us remember the verbal information from the text, and vice versa. For you, that suggests that when you're learning from a map and accompanying text, actively trying to connect the visual elements on the map to the descriptions in the text can significantly boost your memory and understanding of both.
And there are specific techniques that have been shown to improve this kind of conjoint encoding, aren't there?
Ah,
Like actively constructing the map or adding examples.
Exactly. Things like actively trying to construct parts of a map from memory after reading a text, or generating specific examples on the map that illustrate points made in the text. This active, effortful elaboration seems to really strengthen the memory traces for both the visual and verbal information.
Effortful elaboration. Makes sense.
Exactly. This idea aligns with Solomon's earlier work on amount of invested mental effort. The more actively and thoughtfully you engage with the material, the deeper and more lasting your learning is likely to be.
And like diagrams, the visual style of map components matters too. Drawings versus symbols.
Yes. Just like with diagrams, how the individual components of a map are presented visually can also affect this process of conjoint retention. Research comparing maps that use realistic drawings of features versus those that rely solely on abstract labels or symbols has generally found that maps with more realistic drawings tend to lead to better overall recall of information.
Drawings win again.
Generally, yes, compared to maps using only labels or abstract symbols. However, the precise relationship between this effect and the reader's individual reading ability is still somewhat unresolved, with some studies suggesting a greater benefit for lower ability readers and others not finding a significant interaction.
Okay, a bit unclear there.
But the general consensus is that both verbal and spatial encoding are important for remembering information from maps and accompanying passages, and using recognizable and meaningful visual representations on the map can facilitate this process.
The research has also looked into the specific strategies that successful map readers tend to employ. It turns out that it's not just about having a naturally strong sense of spatial ability.
Right, it's more than just spatial sense. Effective map readers often actively use a combination of both spatial and verbal analytical strategies when interpreting and learning from maps.
Like what kind of analytical skills?
Things like being skilled at analyzing terrain features and estimating altitude seem to be important components of map reading proficiency. And these skills often correlate with verbal and mathematical aptitude as well.
And experts use different strategies than novices.
Yes, and studies that have compared expert and novice map readers have identified specific strategies that the experts frequently use. These include mentally segmenting the map into smaller, more manageable regions, forming vivid and detailed mental images of the features and their locations,
Mental imagery.
and actively encoding both the individual spatial relationships between nearby features and the larger, more patterned spatial relationships across the entire map. Interestingly, research has shown that when students are explicitly taught and encouraged to use these expert-level strategies, they tend to recall significantly more information from the maps they study.
Teaching the strategies helps.
Definitely. There's also a distinction to be made between learning the layout of a space by studying a map, which tends to create more scannable mental images in your mind,
Okay, map learning.
and learning by actually navigating through the real environment, which seems to create a different kind of knowledge, a more procedural, how-to-get-there type of knowledge.
Navigation knowledge. Which is better?
Well, for very short exposures to a space, navigation might be more effective for immediate recall, although for providing directions to others, sometimes well-written textual instructions can actually be faster and more efficient than trying to describe a route based on a mental map.
Huh. Text can be faster for directions.
Yeah, it suggests that propositional or verbal encoding can sometimes be more useful than purely spatial encoding, depending on the specific task.
And just like we saw with diagrams, how we are instructed to encode the information on a map, whether to focus on the conceptual relationships or the precise spatial locations, can influence what aspects of the map we tend to remember most effectively.
Right, suggesting that maps convey different types of information that can be processed and stored in different ways.
Okay, now let's focus more specifically on the inherent spatial properties of maps themselves and the particular interpretive skills that are necessary to effectively extract information from them.
Back to configuration.
Exactly. The very configuration of elements on a map, their relative positions, the distances between them, and the overall layout conveys a wealth of information about the territory being represented. And it also plays a crucial role in helping us to organize the information in our own minds. For you, understanding the spatial grammar of a map is key to unlocking its informational value.
And the research strongly supports the idea that having good spatial skills is indeed beneficial for map reading.
How so?
Studies have found that schematic maps of bus routes that accurately preserve the spatial relationships between stops were significantly more effective for solving problems related to route efficiency compared to traditional timetables that lack this spatial information.
Spatial info beats just text tables.
Right. Similarly, after reading a text that described the layout of a building, people's ability to recall the locations of objects within the building was more strongly related to their understanding of the building's spatial layout, as depicted on a map, than to their memory of the textual description itself.
The map layout stuck better than the text.
Exactly.
Oh.
The research has also delved into the specific cognitive processes that characterize skilled map readers. For instance, studies using eye tracking technology have shown that while there might not be significant differences in overall attention or memory retrieval processes between expert and novice map readers,
Okay.
experts tend to have more developed and efficient map-related schemata. Novices, on the other hand, often focus more on simply trying to remember individual names and labels.
Experts have better mental frameworks for maps.
Precisely. Experts also tend to be much better at interpreting topographical maps that use contour lines to represent elevation, likely because they've learned to see these lines as cues that help them chunk the terrain into meaningful three-dimensional features.
It's interesting that even factors like learning style and personality might play a role in map reading abilities. The research mentions some studies about field independence.
Yes, the idea that individuals classified as field independent,
Yeah.
those who are better at perceiving and analyzing individual parts within a complex whole, tended to perform better on certain map-related tasks, particularly among boys, although the findings for girls were less clear.
And gender differences.
There have also been some indications of gender differences in tasks involving correlating maps with photographs and identifying different perspectives of a mapped area, suggesting that there are complex interactions at play and no simple explanations.
Complex stuff.
And it's also worth noting that some research challenges the idea that map skills are purely visual. One particularly fascinating case study involved a congenitally blind child who was able to use a simple tactile map to navigate,
Wow.
suggesting that the underlying spatial reasoning abilities necessary for map use might be independent of visual experience.
So ultimately, it seems that learning effectively from maps requires a diverse set of cognitive skills and strategies. Configuration helps create mental schemata, facilitated by spatial ability and maybe field independence.
Right. And experts in map reading have developed specialized map-related knowledge and know how to effectively leverage specific cartographic features.
And when we look at specific map-related tasks like navigation, the research shows that individuals who have poorly organized internal representations of maps tend to struggle with selecting effective landmarks to guide their way.
Yeah, a bad internal map makes landmark choice harder. This suggests that the way the components are arranged on a map can significantly influence how we develop our own internal spatial understanding and our ability to navigate.
What about route finding?
When it comes to route finding and determining your own location on a map, studies have shown that having the ability to view the whole map at once generally provides an advantage in planning efficient routes, although in very detailed virtual environments, focusing on smaller segments might sometimes be more effective.
Big picture versus zoomed in.
Right. People also employ a variety of different spatial strategies for self-location on a map, indicating that there are individual differences in how we approach this task.
Finally, accurately estimating distances based on a map is a crucial skill, and research has found that our estimates tend to be more accurate when we have either the map or the real landscape present, compared to when we're relying solely on our memory.
Memory estimates are worse.
What helps accuracy?
Factors like using consistent color codes on a map can lead to faster and more reliable distance judgments, and even the pleasantness or memorability of landmarks along a route can influence how accurately we perceive the distances between them.
Pleasant landmarks seem closer.
Something like that, or at least they're more prominent in our mental map. Research on aging has also shown that while older adults might recall fewer map features if those features lack distinctive visual cues, providing clear and salient cues like color and three-dimensional elements can help to minimize age-related differences in both encoding and decoding map information.
So good design helps older adults too.
Definitely. So as we bring this deep dive to a close, it's really striking how well the initial theoretical framework holds up when we look at the extensive body of research on learning from both diagrams and maps.
Yeah, it seems pretty robust.
The fundamental principles of how visual information is structured, particularly the configuration of its components and how easily those components can be visually distinguished, play a foundational role in how we learn and understand this information.
Configuration and discrimination again.
Right, operating both at a very early pre-attentive level and during more conscious attentive processing.
Absolutely. And the two general predictions from the theory seem to be strongly supported by the evidence. First, that effectively leveraging spatial configurations and visual representations significantly enhances our ability to organize and comprehend complex information.
especially for those with strong spatial skills.
especially for individuals who have stronger spatial reasoning abilities. And second, that making the individual components within these visuals as clear and discriminable as possible greatly improves our ability to identify them accurately and understand the overall message being conveyed.
If we were to distill some key insights for you, someone who wants to learn quickly and thoroughly from visual information, we'd have to emphasize the power of well-designed visuals for illustrating relationships and sequences,
Uh-huh.
the utility of graphic organizers as mental frameworks for structuring information, the value of making abstract ideas more tangible through visual representation, and the importance of using familiar and representative visual components.
Familiar components help.
Yeah. It's also crucial to be mindful of the potential for overwhelming detail to obscure the overall message, and to appreciate the significant impact that even simple visual cues like color can have on our understanding and recall.
Finding that balance between detail and the big picture. So as you go about your day and encounter maps to navigate or diagrams to understand complex processes, take a moment to really think about how the design of those visuals might be subtly influencing how you understand and remember the information.
Yeah, look closer.
What aspects now stand out to you after this discussion? Perhaps you'll start to more consciously notice those underlying principles of configuration and discrimination at play, and maybe even identify small changes in the visuals you encounter or create that could make them even more effective for your own learning.
Hmm.
It's definitely something fascinating to continue exploring in the visual world around us.